Thanks for coming. I'm Glenn Seeholzer. I'm going to be giving the second part of the LSU M&S trilogy right now. And I know I had a title up about something about incipient speciation and Andean songbird. That's that guy right there. Unfortunately, the data didn't come together quite quick enough, so instead I'll be presenting a continuation of my work that I presented last year on diversification patterns of phenotypic. So thematically fairly consistent, just not at the phylogeographic level. So sorry about that. And this work's done in collaboration with Santiago Clairmont and my advisor, Rob Bromfield. Alright, so Ferneridae. If you don't know anything about these guys, they are around 300 species, and they're a staple of nearly every single neotropical bird community from Patagonia all the way up through Mexico. What they're not known for is coloration. So if you're looking for a group that has lots of colors, go to Kevin Burns' talk later this afternoon. This is essentially a spectrum of rufous. What they are known for is their morphological variation. So you have all these different phenotypes, many of which are convergent on phenotypes we're familiar with in the Arctic. Others are completely novel. And there's a high degree of foraging specialization. And all these morphologies are really specific to the foraging substrates that these birds are utilizing. And I just want to point out, since we're in Brazil, up in the top left-hand corner, there's the Araucaria tit spinetail, which is specialized on the Araucaria tree. So if anybody's traveling afterwards and goes to the highlands, you'll see that bird up there, or you see the tree, and the bird will be in there. So when we think about morphological divergence, we think about divergence and differentiation at small spatial scales, so competition within communities. And so this is one concept of a niche, right? Ecomorphological divergence. But at larger spatial scales, you might have divergence in habitat preferences. So habitats that are either hot or cold, warm or dry, and all the kind of variation encompassed by those major variables. And Ferneridae also have lots of habitat variation. They're found in the wettest Choco rainforests to the driest Atacama Desert, from the bases of high Andean glaciers right down to the Amazon. And so this prompts the question, all that habitat variation can be summarized in terms of the climatic niche, and these are just kind of the various habitats you find in the tropics. So this would be niche divergence at large spatial scales, at scales of range distributions. All right, so this prompts the question, is ecomorphological or climatic niche divergence associated with diversification? If they both are, what has more explanatory power? And I'm addressing at the phylogenetic scale, and I'm also addressing these questions at the phylogeographic scale. Sorry, enough for this talk. So this question has been addressed in the literature recently in a number of studies that have looked at either morphology or climatic niche divergence. And the way these studies have basically worked is you divide the phylogeny into independent subclades, compute some metric of lineage diversification, and some metric of niche evolution, be it morphological or climatic niche. So here's an example of some of the results. A lot of them find positive relationships. That's a really cool Ferneridae. It's a ground-dwelling wood creeper. Just thought I'd throw that in there. So what I was trying to do in this study is combine these two concepts into a single phylogenetic framework. And to do that, of course, I'm using Ferneridae. And to measure ecomorphological divergence, we have a large data set from Santiago's dissertation of measurements of all the Ferneridae species. And these are 11 morphological measurements of the bill, wing, tail, and foot. And these are all kind of functional units of avian external anatomy tied to a resource acquisition. So with these values, we can compute a size metric, which we define as the mean of the log transform values, and then also a shape metric for each one of the 11 variables, which was the log transform value of that variable minus size. And instead of throwing this all into one PCA and getting a bunch of hard to interpret axes, I opted for a different approach by making these 4 functional PC axes. So the variables for bill, wing, leg, and tail, I computed independent phylogenetic PCAs, used the first principal component, and that became bill shape, wing shape, tail shape, and leg shape. Okay, so for the climatic niche, large spatial scales, we have a really large locality database, georeferenced locality database, from which we've extracted climatic variables. And again, perform a phylogenetic PCA, which will form the tip states for all the Ferneridae. Okay, so for the comparative analyses, I took two approaches. The subclade analysis, which I kind of introduced before, as well as Bayesian mixed models, which I'm sure everyone is familiar with by now. So for the subclade division, I took the MCC tree and essentially drew a line down the tree at a specific age. Everything younger than that line that had at least 5 species per clade, we considered to be a subclade node analysis. Everything that did not meet that criterion, we did not include the analysis. Now, of course, this line can be moved back and forth, so it's somewhat arbitrary where we place that, and we're examining the sensitivity of our analyses to that placement of the line. But for now, the results I'm presenting are with respect to the age of the genus Cranioluca. You can see it up there. And the reason for that will become clear. It's the location of a really well-supported rate shift in the Fernerite tree. We can also do this across the posterior distribution, and we get varying number of subclade divisions between 9 and 20. I've done all those analyses. I'm not going to be presenting them, but they're entirely consistent with what I'll be presenting for the MCC tree. Okay, so the diversification metrics. For lineage diversification, people have used either species richness or diversification rates. If you use a diversification rate, in this context, you're going to be using a net diversification rate, which assumes constant rates of diversification. But we have to test that because there could be density-dependent speciation in these clades, and net diversification might not be the appropriate metric in that case. And it turns out that quite a number of these clades violate the constant rate assumption, and so we just use species richness as our lineage diversification metric. And for the niche evolution, we use the Brownian motion rate parameter for all the variables I described previously. Okay, so here are the results. And there's a lot of dots here, a lot of graphs. All the points are the subclades, and you can see that there's really only 4 niche variables that came out as significant. We have climatic PC1, size, bill shape, and leg shape. And so both morphology and climatic niche are associated with increased species richness. But we're not really sure how these models compare to each other. So to compare them, I compared all the univariate models using AIC criterion and found that climatic niche PC1 was by far the best predictor of species richness. But it may be that climatic niche and morphological evolution combined will have greater effect on species richness than either on their own. And so we put together a really large set of multivariate models, all combinations of climatic niche and morphological traits, as well as crown age. And what I'm presenting here are the top models that are within 4 AIC units of the top model with the delta AIC unit 0. What you can see is all but one have environmental PC1 or climatic niche PC1 as a significant predictor. And the only one that's doesn't have that included is bill shape rate. So from this, there seems to be a strong association with climatic niche divergence and log species richness. And I also want to highlight that these relationships might appear to be driven by that one clade way at the top, that's Cranioluca again. When that's removed, these analyses are the same except size drops out as being significant. Okay, so to get a different perspective on this, we used BAM. And this gives you a lot more power because for the subclade analysis, we had to throw out maybe a third of the species, and this allows us to use the entire tree. And it also allows us to use both constant rate and rate variable diversification regimes in explaining species richness in this group. So, really briefly, BAM gives you an enormous amount of data, posterior distribution of possible rate shifts across the tree. And here I've pulled out the most important of these rate shift configurations. And you can see that a number of them have a rate shift. In this case, it's at the base of Cranioluca, and a few of them don't. And so one way to boil all this information down is to compute Bayes factors on each branch for a model, comparing a model where there is a rate shift versus one where there isn't. And then you can transform the tree based on that. You can transform the tree on the left based on the Bayes factors. And you see that Cranioluca has a well-supported rate shift. We're not exactly sure where, but it's one of those maybe 3 branches leading up into the clade. And that's an example of one of the Cranioluca members. We can also look at this in a different way with the mean of the time averaged speciation rates across the tree. And what we see is that by far there's a really homogeneous diversification dynamic in Fernerinae with the exception of Craniluca. And we have slightly decreasing diversification rates through time, or speciation rates through time. Okay, so we can also do the same thing for our niche traits. So here's leg shape. We see a strong rate shift at the base of the Fernerioids, and the posterior distribution, and of course the base tree, and that's well supported. And what we're looking for here is concordance between the speciation shift, which you see over there on the left in blue, and the shifts in the morphological variables. What we find is we do see shifts in the morphological variables, and I'm happy to go into the details of that later, but we don't see any correlated shifts at the base of Craniluca with the speciation ratio. However, when we look at the climatic niche, we do see this coupling between a shift in speciation and a shift in climatic niche PC1. However, we also notice that for PC1 and PC3, there are two other clades that have rate shifts that weren't recovered as speciation rate shifts in the diversification analysis. And I have good reason to believe that those are due to kind of extreme values in one species in each clade that's driving that relationship. And when those are removed, those rate shifts go away. Okay, so from the subclade analysis, we see that there are significant associations between species richness and both morphological and climatic niche evolution. But climatic niche evolution is the strongest predictor of species richness among all these variables. And from the Bayesian mixed models, we see widespread rate heterogeneity in both the morphology and the climatic niche, and a correlated shift in speciation and climatic niche at the base of Craniluca. So what's so special about Craniluca? Oh, I also want to say one thing. As many of you have probably thought about or noticed, the speciation rates, there's only really two rate regimes in the entire tree. And so we essentially have an N of 2, which makes it kind of hard to do statistical analyses on that. I don't have a good answer for how we progress from here, but there is a really strong coupling between these two things, and I think that's worth noting and recognizing in this group. Okay, so what's special about Craniluca? There's about 28 species that are distributed in essentially all forest environments in South America. And a few of them have some interesting morphological adaptations, but in general they have kind of one phenotype. And so I'm studying the potential drivers of this rapid diversification in Craniluca at this scale, at the clade scale, as well as at the phylogeographic scale by examining one species distributed in the Andes across an environmental gradient from 1,000 meters to 4,800 meters. That shows a wide range of morphological variation. And I hope to be presenting that maybe next year. So, thank you for your attention.
Questions?
Questions?
Yes.
Is climatic niche not part of the geographical area?
It is, but I thought the more interesting thing was that the climatic niche is probably what's the better explanatory factor than geographic area. It's a more interesting way to look at that. Those two things aren't correlated, but when we think about the causality of speciation, geographic area is probably important, but I think adaptation to local environments might be a more important explanation.